Implicit differentiation. Essential question. Can I take a derivative implicitly and solve for dy dx? Let's take a look at explicitly defined functions. You can see this one, I've taken the derivative. It's in terms of x, and I've used the chain rule. Here's another function in terms of x, and I've used the product rule. Here's some implicitly defined relations. They're not necessarily functions. This is our circle, and this is another curve. Let's take a look at the circle. We can take the circle and split it apart into two functions, and that's what we've done in the past. Notice that I was able to take the derivative. I even evaluated it at 3/4 and found the slope was negative 3/4, which seems plausible since it does look like a negative slope. The question is, can I just use this relationship to find the derivative? And the answer is yes. And here's how we're going to do it. What we're going to do is we're going to take this expression and we're going to find the derivative of each term. Now I want to remind you, when we're having something very simple like y equal to x squared, when we find its derivative, this becomes dy dx, and the derivative of the other side is 2x. So keep this in mind as I find the derivative of each term. The derivative here is going to be 2x. This is not something that's difficult for us. Now this is where we're going to have to take a look at y being this expression y squared as a composite function. It's a function within a function, which is going to need the chain rule. The outer function is a squaring function. The inner function is going to be y. So what we're going to do is we're going to take the derivative of the outer function, which is 2y to the first power, which I won't write, and then remember that I have to find the derivative of the inside function, which is y, equals, and then the derivative of a constant is 0. Okay, let's keep going. 2x plus 2y, and now the derivative of y, very similar to what I did over here, is going to be dy dx, and that's going to be equal to 0. Now we're being asked to find dy dx, so we've got to solve for this. So I'm going to take the 2x term to the other side, and that's going to be negative 2x. And now the derivative will be equal to opposite of x over y. Now if I want to take and evaluate at 3/4, that requires me to put a 3 in for x and a 4 in for y. And this was the same derivative that we got on the last screen. All right, let's take a look at finding the derivative at this other curve. And notice that I went through the same steps. I took every term and I found the derivative of each. 3x squared, I used the chain rule here to get y prime. I had to use the product rule here. Notice that the derivative occurs in two terms. I'm going to get those two terms on one side, the other terms on the other side, and then solve for y prime. And so that's the steps in going through to find it. The last part of the question asks us to find where we have a horizontal line tangent. Horizontal line tangent. Our tangent line horizontal. Okay, before I go to the next screen, visually I can see that there might be a horizontal line right about here and possibly right about here. So let's take a look at the steps that require that. I am going to be looking at the numerator of my derivative, and I'm going to set it equal to 0 because that's how we get horizontal tangents. And when I do that, it simplifies to y equal to 1/2 x squared. And this is the expression that I'm going to put in here and in here. And this is from the original relation. I'm going, everywhere I see a y, I'm going to write that because that's the requirements for a horizontal tangent. It's going to simplify to this, and then I can solve and get x equal to 0 and x equal to be cube root of 1/16. And so when we solve for that, we're going to find that x is here, which that's kind of where we assumed it was going to occur. And of course, it's no surprise that it's also at the origin as well. All right, here is another example. You might want to stop the screencast to take a look at it. But the derivative of the first part is going to require the chain rule, and here's that y prime showing up, treating y as a differentiable function in x. And the right-hand side, we're going to use the product rule, and again, the y prime shows up here. We're going to distribute to get two terms on this side. Two terms will be on this side. We'll get all the y prime terms on one side and all the terms that don't have y prime on the other side. Solve for y prime, and we're going to get this complex expression. What's interesting about it is at the origin, right here at the origin, if I were to substitute 0 in for x and y, I will get -1. And sure enough, the slope at the origin does look like it's -1. All right, let's take a look at finding a second derivative. Now the first derivative has been done for us, and now I am in the process of finding the second derivative. And notice that I'm having to, what I did is I wrote it this way so that I could use the product rule. And I found the derivative here, and my answer has a y prime in it. And so this is the step at which I want to help you at. What we would like to do is have it only in terms of x and y and no derivative. So when you see this y prime, what you can do is you can substitute what y prime is. Here's y prime, that's what it's equal to. So I'm going to write opposite x cubed y to the -3. And now everything is in terms of x and y. You might want to clean that up before you use it. Okay, let's talk about derivatives of inverse functions. Now remember, the characteristic of an inverse is that it's a reflection over the y equal to x line. So here's our function, and here's our inverse. Notice x's and y's exchange places. Domain and ranges exchange places. So here's our x and our y, and here's, you see the x and the y here, they're just replacing each other here, which makes sense for an inverse. Look at the quality of the graph. You can see it looks like a reflection as well. Now, let's talk about derivatives. Now, remember, derivative is a slope. So this is going to be delta y, delta x, and then over here, remember, things have changed places, delta x, delta y. So it should be no surprise to you that the slope here and the slope here are reciprocals of each other. And so one is equal to 1 over, the slope is equal to 1 over the slope of the other. Some people just say reciprocals of each other. Some will say that the slopes multiply to be equal to 1. Okay, let's utilize this fact in this exploration. We have the function right here, and we would like to find the derivative at 2, the derivative of the inverse at 2. Now this is f of x, and here's the point 1, 2, right here, 1, 2. Now its inverse will be the reflection, so I'm just going to try to reflect here. And this will be f inverse of x. Now the point that I'm looking for is the point where x and y have exchanged again. So this is the point 2, 1. And that's what I'm being asked to do, is to find the derivative at 2. Well, the clue is if you can find the slope here, then this slope will be the reciprocal. So let's go ahead and do that. F prime of x will be equal to 5x to the 4th plus 2, and its value at 1 will be equal to 7. So I know that the derivative of the inverse at 2 with respect to x will be equal to 1/7. Remember, these two have to be reciprocals of each other. All right, let's take a look at a problem where we don't have the graph here. So here we have f of 1, and f of 1 is going to be 1 plus 2 plus 1 minus 1, and that ends up being 3. And let's go ahead and figure out the derivative, which is 5x to the 4th plus 6x squared plus 1, and evaluate it at 1. This will be 5 plus 6 plus 1, which is equal to 12. Now, this is the point 1, 2, so it should be no 1, 3. So it should be no surprise that in the inverse, this value right here will be equal to 1. Remember, like we had in the graph, the x's and y's are going to reverse each other. Now, the slope at 1 is 12, so it should be no surprise the slope here will be the reciprocal, which is 1/12. Let's take a look at other inverse functions, and these are the inverse trig functions that we did through the trig review. Let's now talk about the derivative at each one of these trig functions. So this is the inverse trig functions, and remember the domain and range. The range has to be limited so that it is a function. And I'm going to draw a triangle at the 4th quadrant and the 1st quadrant, because those are where my angles are going to be coming out of. They're going to be coming out between negative pi halves and pi halves. So this is an example. Remember, an inverse sign is giving you an angle. Let's go back to the symbol that doesn't have the inverse. So let's go back to this, and let's find the derivative implicitly. So I'm going to take the derivative of cosine, leave the inside alone, times the derivative of the inside function. And so here is what I'm trying to find. I'm trying to find dy dx. So I put the cosine on the other side here. Now, this is in terms of y. We would like it in terms of x. So here's our picture. Here's y. Here's the angle. And remember, over here, we were told that the sine of y is equal to x. The sine of y is equal to opposite over hypotenuse. So that's how I got the picture, is I used that. Now the question is, what's this length right here? Well, we're going to use the Pythagorean theorem, and this will be root 1 minus x squared. This is what I need to be able to find the cosine of y. So the cosine of y is adjacent over hypotenuse. So right down here will be adjacent 1 minus x squared divided by hypotenuse. And that will simplify to just this. Now this is just a positive answer. It's 1 over root 1 minus x squared. And if you look at the curve right here of sine inverse, notice that all the tangents are always positive. So this formula makes sense for our graph. Now the same thing can be done for y equal to tan inverse. What we're going to do is we're going to rewrite it so it doesn't have that inverse symbol. We're going to use implicit differentiation, and we're going to take the derivative of the outer and then times by the derivative of the inner, which is going to yield this. And then I'm going to say dy dx is equal to 1 over secant squared y, and then we're going to use an identity to substitute. And what is right here, tan y is equal to x. So I'm just going to replace it with x squared. And this will be the formula for the derivative of tan inverse. Now this is also a positive quantity, and notice the derivatives here are all positive. If I were to graph 1 over 1 plus x squared, I would get this curve right here. This is telling you the slope. And you can see that the slope at 0 is the steepest, and the slopes there going to infinity are getting less steep, and going to negative infinity again getting less steep. Okay, here's some examples of differentiating with sine inverse. Notice that I had to use the quotient rule, and when I use the quotient rule, I got this expression right here. Over here, I have y equal tan inverse of root x, and I had to use the product rule. This right here required me to use the chain rule. So I had to do 1 over the argument squared, and then I had to take the derivative of the argument, which is 1 over 2 root x. And I simplified and got this. Here's a summary of all the derivatives of inverse trig functions, which need to be memorized. Notice there is a pattern. If you learn half of them, the other half have a negative in front of it.